Now, today we will discuss continuity and differentiability. Here, topics to be discussed are continuity, differentiability, exponential and logarithmic functions, logarithmic differentiation, derivatives of functions in parametric forms, second order derivative. Continuity. A function is continuous at x is equal to c if the function is defined on is defined on a function f is continuous at x equal to c if the function is defined on x is equal to c and the value of function at x is equal to c, that is fc, equals to the limit of the function at x is equal to c. Limit x tends to c fx. You know that limit x tends to c fx exists if left hand limit and the right hand limit for x tends to c exist and are equal. Let us do some questions. So the question is, discuss the continuity of the function fx is equal to mod x at x is equal to 0. Solution. We know that mod x is minus x if x is negative and x if x is positive or 0. So here c is 0. Let us draw its graph. You can see this is x-axis, this is y-axis, and this is the graph of mod x. You can see there is no any breakage. So continuity means the graph having no breakage. It means from the graph you can say the function mod x is continuous at x is equal to 0. This is 0. Here are 1, 2, minus 1, minus 2, and above 1, 2, minus 1, minus 2. Now let us do the question analytically. So here, according to the definition, the function should be defined at c. Clearly f is defined at 0, means its value is 0. Defined means the function should give a real number value at the given value of x. Now fc means f0. You can write f0 from this. This is 0. You have to write limit. Here you can you have to write left hand limit and right hand limit, because here when the x is less than 0 the function is minus x. So limit x tends to 0 minus. You know that limit x tends to 0 minus means x tends to the value nearer to 0 from left side. So this is minus x, and you know that this one is minus 0 is 0. Now right hand limit. Here x tends to 0 from right side and nearer to 0. This is x. You know that this is equal to 0. Therefore, limit x tends to 0, fx is equal to limit x tends to 0 minus fx, limit x tends to 0 plus fx, both are equal, that is 0. So this is the value of the limit. 0 is the value of the limit, and you have discussed that fc means f0, which is 0, and it is equal to the value of the function at the c, means fx. This implies that f is continuous at x is equal to 0. Let us do the next question. So that the function f given by fx is equal to x square plus 3 if x is not equal to 0, 1 if x is equal to 0, is not continuous at x is equal to 0. Solution. Here c is 0, so we write f0. f0 is, for x is equal to 0, function is 1. Now let us discuss limit. Here for both sides of 0, that is for left sides and right side of 0, this is the value of fx, so there is no need to write left hand limit and right hand limit separately. Directly we will write limit x tends to 0 fx. Limit x tends to 0, here fx is, here x is not equal to 0. You know that x tends to 0 is not equal to, x is not equal to 0. So x square plus 3. Now you put the value of x as 0. So 0 plus 3 is 3. You can see here f0 is not equal to limit x tends to 0 fx. It means that clearly f0, which is 1, is not equal to limit x tends to 0 fx, which is 3. Hence f is not continuous at x is equal to 0. Continuity in the domain. A function is said to be continuous if it is continuous at every point in the domain of let us do a question. So the third question is the function fx is equal to mod x a continuous function? See here, there is no given any point c. It is asked whether in the domain of mod x. You know that the domain of mod x is set of real numbers. So it is asked that whether in the domain of mod x it is continuous. From the graph of mod x, you have already known that it is everywhere continuous. But let us do it analytically. Solution. You know that fx is equal to mod x is minus x if x is negative and x if x is positive or 0. So we have already shown that as before we can show that f is continuous at x is equal to 0. And now we have to discuss on LHS on negative values of x, whether f is continuous. So we can take arbitrary number. Let c be a real number negative real number. Then for this C, which is x, fx is minus x. Then fc is equal to, since c is negative, so minus c. Now let us discuss the limit. So limit x tends to c fx. This is x tends to c. Here c is negative, so fx is minus x. This gives us minus c. So you can see fc and limit value of function and limiting value of the function are same. So we can say clearly f is continuous for negative real number. Now let us prove for positive real number. So let C be a positive real number. Then fc is equal to c. Now limit x tends to c fx. This is equal to limit x tends to c fx is x. For positive real number c, fx is x. So this is c. So the value of function for a positive real number and limiting value of the function at positive real number are same. So clearly f is continuous for positive real numbers. Thus we see that f is continuous everywhere, that is in domain set of real numbers. Thus f is continuous in its domain. So the next question is, discuss the continuity of the function f defined by fx is equal to x plus 2 if x is less than or equal to 1, x minus 2 if x is greater than 1. This is our fx, x plus 2 if x is less than or equal to 1. The function f is, the function is defined at all points in its domain. You can see now for values lesser than 1, it is x plus 1, so case 1. If c is less than 1, we have to discuss its continuity. Then if c is c plus 2, now let us discuss its continuity. Limit x tends to c fx. When c is less than 1, so x plus 2, this gives us c plus 2. Thus f is continuous. You can see fc and limit x tends to c fx are equal, so f is continuous for c less than 1. Case 2, if c is greater than 1, then fc is equal to c minus 2. It is given that when x is greater than 1, fx is x minus 2. Limit x tends to c fx, limit x tends to c x minus 2. This is c minus 2. So they are equal. Thus f is continuous for c is greater than 1. Let us discuss the case 3. if c is equal to 1, then by the definition, when x is equal to 1, fx is x plus 2. So f1 is x plus 2, 1 plus 2, this is 3. Now let us discuss left hand limit and right hand limit, because for the left side of 1, fx is x plus 2, and for the right side of 1, fx is x minus 2. So limit x tends to 1 minus fx. This is limit x tends to 1 minus x plus 2, 1 plus 2, this is 3. Now right hand limit x tends to 1 plus fx. Limit x tends to 1 plus. For values greater than 1, fx is x minus 2. So 1 minus 2, this is minus 1. We see here left hand limit and right hand limit are not equal. Clearly, left hand limit is not equal to right hand limit. This implies that limit x tends to 1, fx does not exist. At c is equal to 1. So x is equal to 1 is the only point of discontinuity. Let us check it with the help of its graph. Here doubtful point is 1. You can see at 1, 1 plus 2, 3, this is 1, 3. And as x is less than 1, fx is x plus 2, so graph varies in this way. Here x greater than 1, when x is greater than 1, this point is blank, because at x is equal to 1 it is 3, and here this point is 1 minus 1, but this is blank. And to the right of 1, fx is x minus 2, so the graph proceeds in this way. You can check values. If you take x2, then it passes through this one, that is 0, y0, this is 2 comma 0. After joining and proceed, this is the graph. From the graph you can also say that its left hand limit is at 1 is 3, and its right hand limit is minus 1. So they are different. So, and if you draw the graph of this function, we need to lift our pen or pencil. So the function has breakage at x is equal to 1, and so this is the point of discontinuity. Find all points of discontinuity of f, where f is defined by fx is equal to mod x plus 3 if x is less than or equal to minus 3, minus 2x if minus 3 is less than x is less than 3, 6x plus 2 if x is greater than or equal to 3. Here the domain of the function x breaks at minus 3 and 3, so there are only 2 doubtful points. X is equal to minus 3 and x is equal to 3. So let us discuss at x is equal to minus 3. We can say generally a function is discontinuous at a point if this one left hand limit is not equal to right hand limit, and the second, if the limit exists, then the value of the limit is not equal to the value of the function. So let us see what happens here, whether it is continuous at minus 3 or not. So firstly, here we can see to the left of minus 3, this is the function. To the right of minus 3, this is the function. So we have to take left hand limit and right hand limit. So limit x tends to minus 3 fx is equal to limit x tends to minus 3 minus fx is mod x plus 3. Here x is less than 0, so mod x is negative. So when we remove the mod, minus sign comes. Now x tends to minus 3, so we put the value. We have minus 3 plus 3, this is 6. Let us find right hand limit. Limit x tends to minus 3 plus fx. Limit x tends to minus 3 plus. Here fx will be minus 2x. Here we take fx when x is greater than minus 3. Then fx is minus 2x, so minus 2 into minus 3. This is 6. We see that the value of the limit is. Therefore, limit x tends to minus 3, fx is equal to 6. Now, f minus 3. When x is equal to minus 3, fx is mod x plus 3. So, mod minus 3 plus 3, this is equal to 3 plus 3 is 6. Therefore, f minus 3 is equal to limit x tends to minus 3 fx, both are 6. So x is continuous, so f is continuous at x is equal to minus 3. Let us check it on other points. At x is equal to 3. Here you can see to the left of 3, this is fx. To the right of 3, this is fx. Minus 2x and 6x plus 2. So we have to find left hand limit and right hand limit separately. Limit x tends to 3 minus fx. Limit x tends to 3 minus 2x. Minus 2 into 3, this is minus 6. Limit x tends to 3 plus fx. Limit x tends to 3 plus, when x is greater than 3, fx is 6x plus 2. So 6 into 3 plus 2, this is 20. Therefore, clearly, limit x tends to 3 minus fx is not equal to limit x tends to 3 plus fx. Imply that 3 fx does not exist. Hence, f is discontinuous at x is equal to 3. See students, why I have written there are only because we know that if we take values lesser than minus 3, then this will be continuous. More than minus 3 and between 3, then this also be continuous. And more than 3, then this also be continuous. We have shown such type of continuity earlier, so there is no need to show. So we write there are only two doubtful points, and that will these doubtful points will be taken from the breakage of domain, so that every polynomial function is continuous. We know that polynomial function p is defined by px is equal to a0 plus a1x plus a2x square dot 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 an x to the power n, where n is a natural number, n is not equal to 0, and ai belongs to set of real numbers. These are ai, n, a2, a1. So we have to show, let's see be a real number. Then we take a limiting value x tends to c px. So limit x tends to c a0 plus a1x a2x square plus dot 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 an x to the power n. This will be, we put the value x is equal to c, we have a1c plus a2c square dot 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 an. This is pc, the value of the function at c. So the limiting value of the function is equal to the value of the function at c. Hence the result. Find all the points of discontinuity of the greatest integer function defined by fx is equal to greatest integer x, where greatest integer x denotes the greatest integer less than or equal to x. So let us draw the graph to understand clearly. Here, suppose we take the values 1 or more than 1 but less than 2, then we have 1, because greatest integer x is the greatest integer less than or equal to x. If you take 1.5, then greatest integer less than 1.5 is 1. If we take 1, then greatest integer will be 1, because or equal to x is here. So if x is integer, then that is the value of greatest integer, and if x is integer, if x is not integer, then the value will be greatest integer less than x. So if we take the value minus 2, greatest integer minus 2, then it will be minus 2. And if we take greatest integer more than minus 2, suppose we take a minus 1.5, then greatest integer minus 1.5 will be the greatest integer less than minus 1.5, then it is minus 2. So this darkened part show the graph here. Greatest integer 2 is 2, so this circle is hollow and this is darkened, and the value greater than 2, the greatest integer is the value greater than 2 but less than 3, the greatest integer is 2. So there are two cases. First, let C be a real number and not an integer. Then limit x tends to c fx. Limit x tends to c fx is greatest integer x. This is greatest integer c, which is fc. You can verify this using example. Suppose you take c as 1.5, then here we have 1.5, then we have the greatest integer 1.5 is 1, and this is also fc. fc means greatest integer c, which is 1. So f is continuous at non-integral value. Let us see. Let c be a real number and c belongs to the set of integers. Then from the graph, suppose we take 2, then to the left of 2, the value of greatest integer is 1, and to the right of 2, the value of greatest integer is 2. So we can say, we can take another example also. If we take c as 1, then to the left of 1 we have greatest integer 0, and to the right of 1 we have greatest integer 1. So here left hand limit and right hand limit vary. Then limit x tends to c minus fx is equal to c minus 1. Let me elaborate this step. And limit x tends to c plus fx. Limit x tends to c plus greatest integer x. This is c. You can see they vary. Clearly, limit x tends to c fx does not exist. Hence, f is discontinuous at all integral values. Now algebra of continuous functions. Theorem 1. Suppose f and g be real functions continuous at a real number c, then first f plus minus g is continuous at x is equal to c, means the sum of the functions is continuous at x is equal to c, and also the difference of the function is continuous at x is equal to c. Their product is continuous at x is equal to c. Their quotient is continuous at x is equal to c, provided the denominator is not equal to 0. Proof. First, clearly f plus minus g is defined at x is equal to c. Now we have to show the limiting value is equal to the value of the function. So limit x tends to c f plus minus g x. This is limit x tends to c fx plus minus gx by the definition of f and g. From here we can write fc limit x tends to c fx plus minus limit x tends to c gx by the theorems on limits. From here we can write fc plus minus gc. From here we can write f plus minus G C by the definition of F plus, by the definition of F plus minus G. Hence, F plus minus G is continuous. Similarly, other parts of the theorem can be proved. Discuss the continuity of sine function. Solution. Clearly, sine function is defined for any real number C. Now we have to show that the limiting value of the function is equal to the value of the function. So put x is equal to C plus h. Then limit then x tends to C implies, suppose x tends to C, then h tends to 0. Limit x tends to C fx. Here fx is sin x. Limit x tends to C sin x. Now as x tends to C, h tends to 0. Limit h tends to 0 sin C plus h. We know that sin C plus h is sin C cos h plus cos C sin h. Here we have limit h tends to 0 sin C cos h plus limit h tends to 0 cos C sin h. Then we have sin C here, limit h tends to 0 cos h, cos C limit h tends to 0 sin h. This is sin C and this one is 1 plus cos C, and limit h tends to 0 sin h is 0. So we have sin C. This is our FC. Hence, f is continuous everywhere. We have also seen the graph of sin x, that is everywhere continuous. Similarly, we can express the continuity of, we can establish the continuity of cosine function. Here, prove that the function fx is equal to tan x is continuous. So we know that tan x is equal to sin x by cos x is defined for all x belonging to R except those values of R where cos x is undefined, that is 2n plus 1 pi by 2, 2n plus 1 pi by 2, where n belongs to set of integers. So tan x is defined on the all values of real numbers except odd multiples of pi by 2, except odd multiples of pi by 2. Clearly, sin x and cos x are defined in the domain of tan x and are continuous wherever defined. Now, tan is the quotient of two continuous, the domain of two continuous functions, hence it is continuous wherever defined. Theorem 2. Suppose that f and g are real valued functions such that f of g is defined at C. If g is continuous at C and f is continuous at GC, then f of g is continuous at C. Let us elaborate it using diagram. Here g and f are two functions where c at c g is continuous and its image is GC, and GC has image under f has FGC. This is FGC. Now this is the function f of g, the composition of g. According to the theorem, if g is continuous at C and f is continuous at GC, then f of g is continuous. F of g is continuous at C. So that the function fx is equal to mod cos x is a continuous function. Solution. Clearly, f is defined for all real number. Now this is a composition of two functions. So we have to suppose, we have to think, then we can write let gx hx. Then we have to write gohx, which should be mod cos x. You can say if you take hx cos x, g cos hx. If you take hx as cos x, then you can write this as mod cos x. Here you have to take cos x, here you have to take mod x. Clearly, that's clear. Then gohx is equal to mod cos x. Is that clear? Here g and h both are continuous functions. Here g and both are continuous functions. Hence, their composite GOH is also continuous by the theorem. So that the function fx is equal to mod of 1 minus x plus mod x, where x belongs to R is a continuous function. Solution. Clearly, f is defined for all x in R. Now we have to check gx and hx such that gohx is equal to fx. So if we take hx as 1 minus x plus mod x, then we have 1 minus x plus mod x, and this is mod x. Then we have mod of 1 minus x plus mod x, which is equal to fx. Now g being modulus function, hence it is continuous, and h being the sum of polynomial 1 minus x and modulus mod x, and h being the sum of 1 minus x and modulus mod x, hence it is continuous. Also, f being the composite of g and h continuous functions, hence it is continuous. That's all for continuity.